It's recording. Okay.
Okay, well, thanks very much. Thank you very much for the introduction, and thank you for inviting me to deliver a talk on this workshop. The topic is, I'm trying to see if I can provide an overview, high-level overview, what could event-based cameras be used for in multi-agent scenarios. And thank you very much, Andrea, for the previous talk and the introduction of already the topic of visual inference. So let's see if I go to the next one. Not working. Okay, can you hear it?
And yes, now it's good.
Okay. So the first thing is like to be all on the same page is to know what an event camera is, right? And I think one of the easiest ways to understand what an event camera is to look at the difference with classical cameras. So here we see a video acquired with a normal video camera, standard one frame-based camera, and that is more or less happening at 6 Hertz, so 6 frames per second. In a normal camera, we are acquiring these images using an external clock. The external clock tells the pixel to expose and then acquire light. And in contrast, event-based cameras, they do not listen to an external clock. They just capture the data that we see here with these red and green dots as it happens. So they are basically trying to sample the scene based on the scene dynamics. And we see it's a much more continuous signal representing the motion. What we see is also that only the pixels that are actually changing on this part of the image plane of the field of view are actually producing these so-called events, which are brightness changes. The rest, the ones that are not changing intensity, they don't produce this signal. So if we take a look and try to visualize what the signal looks like in space-time and the image plane, here we have a camera with 240 pixels by 180, and we are visualizing 160 milliseconds of data, and the color represents time. So green is old time, as you can see from the trajectory of the ball, and red means recent time. We can actually see more or less the silhouette of the tennis player. And what we observe is that the data that comes is quite unfamiliar. It doesn't consist of images. It's mostly these dots in space-time, which are the so-called events, brightness changes, and they come asynchronously with microsecond resolution, and they are a sparse signal, as opposed to the dense signal that we typically consider regular images. So these are some characteristics of the data produced by event-based cameras. And actually, event-based cameras are bio-inspired sensors, and they try to mimic the model of the transient visual pathway in humans. And this, how it all starts is that you try to know how biology works. So you look at the retina, and you come up with a simplified model of the different layers of the retina. In this case, just a 3-layer model of it with photoreceptor, bipolar cells, and ganglion cells. And then you try to mimic it with a circuit. You try to implement on silicon. And here is the circuit with the different phases. So the blue part is the photoreceptor, the green is the bipolar, which is some amplification and resetting. And the last part, the red, is the ganglion cells. Then once you have this circuit, I mean, there are a lot of iterations going on, but then you say, how does it react to incoming light? Where when light comes at a pixel, every pixel works independently, it will produce this blue signal on the top. And that's the part that goes in the first part, the photoreceptor, and then it goes to the next stages of processing. And basically what happens is that there is integrating light with the second stage, and whenever this light that is integrated reaches a threshold, either because it's a positive threshold or a negative threshold, then it will create these so-called events, or in terms of neuroscience, they would be called spikes. So the on spikes are the positive or brightness increase, and the off spikes are the negative ones, the negative brightness decrease. And the output of the camera is basically these events that have, as you can see here, X, Y coordinates of the pixel where it happened, the timestamp when it happened, and P is the polarity, is the sign of the brightness change. And finally, what you do is that you implement this circuit and on a VLSI, and there's this camera. So the first camera that was commercially available and successful with this model is the dynamic vision sensor. It's around from 2008 from Professor Tommy Delbrus group. Now we fast forward, move to 2020, 2021, and we have all these players, all these companies and cameras going on. Here you see that each column is a different company or a model from the company, and the rows are the characteristics of the sensors. And we see that there are some startups, Innovation Prophecy, and also big players that either are there for a long time ago or because they bought some startups such as Sony or Omnivision. They acquired Insightness and CellPixel respectively. So in this big table, what we see is that the pixel pitch, the size of the pixel has been constantly decreasing. We are entering this megapixel race because now in 2020, 2021, we have about 1 megapixel, 2 megapixel event cameras. The field factor, so the amount of area that each pixel is exposing to light, to convert light, has been increasing, and now we have backside illuminating sensors. And besides the improvements on the pixels, what we also notice is that some kind of additional output, like grayscale, trying to produce some grayscale signal or combine it with an inertial sensor, it's also all integrated in the same camera. So today, event cameras are kind of becoming a commodity. They are still expensive, about 1,000 euros, like 4,000 to 6,000 euros, but available, much more than neuromorphic processors. And yeah, that's one of the good things, that being able to acquire these sensors is getting people to work on the problems with these sensor modalities. And nowadays, event cameras, we know that they are kind of used as fast and high dynamic range visual imagers. So what we see in the video is that these are reconstructed videos from events using an algorithm, in this case, a neural network. And what these videos expose is the large amount of data that the events alone contain, right? If you get the events, you process them with some algorithm, you are able to acquire this slow motion video, nearly 5,000 frames per second, showing the high temporal resolution, the high speed of the sensors, the capabilities. And also on the bottom, we can see the high dynamic range. On the left would be that you are able to see inside and outside the tunnel due to the characteristics of the sensor. And on the right side, with a regular camera, it's not possible to see both inside and outside the tunnel because there is no single exposure time that you can adjust to see both. Okay, so now having consumed quite some time on introducing the sensor, I would like to talk about the two main scenarios where they are used, and we see them in this slide. So when the event camera is static, we see that most of the events, except for some background noise, is coming from the parts of the scene that are moving. In this case, somebody waving the arm in front of it. The pixels that are not producing events are silent, and that's one of the reasons why these are low power sensors. They are only trying to focus their attention on the parts that are changing in the scene. And in contrast, when we move the camera around, the events are coming from edges, right? Edges are the ones that are causing these brightness changes, but we see that because of the induced ego motion of the camera, events are happening everywhere. And this is not so much the ideal condition for event cameras, because now a huge amount of data is generated with depending on the pixel resolution and at the microsecond time resolution. So we are burning a lot more power into acquiring this signal. Still, it's an interesting sensor for this scenario. So what are some of the challenges I guess in autonomy, to enable autonomy of agents, are robustness to difficult scenarios such as high speed, high dynamic range, and also efficiency, because if we build an agent like the robot we've seen before, it has limited capabilities. It has limited sensing and limited processing resources and power. We try to address these challenges with event cameras, trying to come up with a bio-inspired point of view. And they are indeed revolutionary technology, that offers many advantages, as I think I've shown in these previous videos, and many opportunities in different applications, which I will try to cover. But because the working principle is slightly different from the one that we are used to with frame-based cameras, it's still light, but we are not sampling light in the same way that we usually do in computer vision. It basically requires us to rethink the methods that we use to process that data. And therefore, the question is, how do you optimally process the events to solve a given task? In the case of stationary cameras, as I said, this is kind of like an ideal situation. Here, they can be used for surveillance, for remote sensing, for monitoring. This is a camera looking at the lobby of a hotel. The grayscale images, they are acquired by frame-based cameras, but then on top, we also have an event-based sensor that is picking up on these parts of the scene that are changing. And if we count how many events are generated, we see that when nothing is moving, the event rate is very small. And even when things are moving in the scene, the data that is acquired and transmitted is much smaller than the data that you would have if you were to acquire frames at such a high frame rate. And well, now looking at this type of data, we see that because the events are only picking up on the things that are moving, the dynamic parts of the scene, it's basically doing an in-hardware background subtraction. It's quite easy to define a tracker that would tell us about the behavior of these multiple agents in the scene. Could be robots, could be humans, could be animals. But in the scenario of a static camera, if there are no flickering lights going on, basically the events are triggered only by the moving parts of the scene, and it's kind of a nice scenario to track objects easily. And in fact, this is one of the first applications that Samsung had in mind when they are developing the first commercial product, the Smart Things Vision. That is kind of this device that you put in your house with an event camera, and it has a light, and it will analyze the data and will try to come up with an alarm system if it detects the behavior, such as somebody is falling or somebody entered your house, there is an intruder there, because the signal that it's basically analyzing, as you can see, it's mostly coming from the moving parts of the scene, and therefore it's kind of easy to pick up on that. Now, in this regard, I would like to also mention this recent work that is also for monitoring and remote sensing. This is, as we said, event cameras have quite some advantages: low power consumption, temporal data redundancy, high temporal resolution, and high dynamic range. For the scenario of monitoring outdoors is also quite interesting. So therefore, this is a data set from last month at CVPR workshop, where they acquired outdoors scenes with different background noise, challenging illumination conditions, and they also labeled the data set. They have 3 event cameras and a kind of playground area outdoors. And for long-term recording. And as we can see, these are the type of environmental interferences, such as rain, clouds, eco motion, sometimes when the camera is shaking, or other disturbances, shadows. And it's funny how to see that things such as birds and insects flying around, they are captured, and this could be used to analyze them. And actually, the data provides label for these classes: people, bicycle, dog, and sports ball. I think this is a nice data set that can be used to develop methods for multi-agent on remote sensing using event-based cameras. Now, moving to the second scenario with the moving camera, we've seen the events are occurring everywhere on the image plane. And I would say that if you want to have autonomous agents, they need to know where they are in the environments and to try to understand it. And it's kind of what Eduardo was saying at the introduction. We need to provide another layer. Well, I think we are still in this layer where we are trying to solve SLAM problem, and which is slowly becoming the spatial AI with more ingredients on it. So here we have a monocular SLAM, or event-based visual odometry, 6 degrees of freedom on the CPU. On the bottom right are the events collected as an image, but this is a space-time signal. And on the top left, it's the output, which is a map of the scene that works even in high dynamic range conditions against the sun. And here's another example where we are actually moving the camera and building a map of the scene as the camera is moving. On the bottom right, we see the input events and the frames, but we are not using the frames. And yes, we are building this map, comparing it to ground truth, doing a good job. And what we visualize in the middle is this high dynamic range reconstructed image. And we see that when we turn the lights off and on, because the events have a very high dynamic range, we are still able to track our system, and we are also able to use the output of our system to generate these reconstructed images. And the code, it's available online. You can go download it, try it, and play around with it. So that's with one camera. With two cameras, we also work on it, and we have this event-based stereo visual odometry system in collaboration with Hong Kong. And the idea is similar, is try to do efficient algorithms that run in 6 degrees of freedom motion, and we'll input the events that are somehow converted into an intermediate representation called time surfaces. And the output would be the trajectory of the camera and the map, the depth map or a 3D point map of the scene. And it's working in a kind of classical way, having a worker that is doing the mapping part, the depth estimation, and another one that is doing the tracking part, the ego motion estimation of the camera given the map. And in context of multi-agent scenarios, we tested our system, whose code is also available, on this recent data set from the University of Zurich called DSEC, published at RAL. And yes, so the input are the events from both cameras, and the output is the trajectory of the camera and the estimated depth map of the scene. And it's a huge amount of data now that cameras are going into the VGA or megapixel resolution, but still our system is able to produce trajectories that look like the real one. I think we are still waiting for ground truth data to be published in this data set. But so driving scenario is one of the ones that multi-agent is targeting, and event-based cameras could be used, for example, in difficult situations where normal cameras would not be providing a good result. And I would like to move to the last part of my talk to discuss a bit how to process the events. We said that these are the challenges. We have this sensor where we try to improve robustness to difficult conditions and be efficient. And the key question if you start using events is how do you process this new type of data? And there are many, many different methods, and I cannot cover all of it in the time of a talk or in the time of a day. So I will just talk about one that I'm particularly fond of, that I have been working for quite some time, and is called contrast maximization framework, or also focus maximization framework. And I like it because it's a framework that it can be applied to solve multiple computer vision problems using event-based cameras in a unified way. So the same theory can be applied to solve optical flow estimation, 3D reconstruction, motion segmentation, etc. The reference is right here at the bottom. The main idea it's the following. We've seen what this data is. This is the data produced by an event camera in some space-time volume. We see the X and Y coordinate of the image plane, and we have a few milliseconds of data. And each of these dots, the blue dots or the red dots, they represent a brightness increase or a brightness decrease. It doesn't look like there is much information here. It looks like it's difficult to extract any information about it. We know that events are triggered by edges, but it's hard to see them here or to recognize them. So the idea would be to try to see them from a different point of view, in this case, or try to count them along these motion trajectories, work the space-time volume of events, and so that we try to maximize the focus, the sharpness of the resulting image. Here it's shown with a 3D representation that there is really like basically we are trying to count how many events happen along these trajectories. So this is the input data. Then we hypothesize, we say, okay, let's try to count how many events happen along these motion trajectories. And if we count the events, we will come up with an image of warp events that it's basically the count along each of these curves. And then we measure how well the curves align with the event data. So we somehow come up with a measure of the edge strength of the image of warp events. And finally, what we need to do is that we need an algorithm that will try to go uphill the score and try to obtain what is the maximum score, the motion parameters that maximize the edge strength of these candidate image of warp events. So that was in 3D, but if you actually look at what are the intermediate results of the optimization algorithms, you see at the beginning that the image of warp events, counting how many events happen at each pixel, it's kind of blurred, looks like a blurred image, and it has to be like that because the events are caused by when an edge is moving on the image plane. Now the thing is that instead of counting how many events happen at each pixel, like it would be here, what we are trying to do is trying to count them in different directions, so as that to kind of bring this thick edge, as you would say, into a single pixel. That would be when you have estimated the motion parameters that best match the trajectory of the edge that was causing the events. And this is with polarity, and it also works without polarity. So in the case of how to apply this to 3D reconstruction, this focus maximization idea has obvious connections with shape from focus in images. So on the left, we are basically sweeping through the space in front of the camera. We have a camera that is moving, and we know the trajectory of the camera, but we don't know what's in front of the camera. We don't know the 3D scene. And what we do is that as events are triggered, we try to back project these events into space. And we see that the events are intersecting. They are becoming into focus at the correct depth where they should happen. So the events that correspond to the Arc of Triumph are closest to the camera, and we see that they are here lining up. Then there is the box, and towards the end, towards the of the plane sweeping strategy, we have the events that become into focus when they are triggered by the darts. And on the right, we see what would happen if we extract the local maxima in this disparity space image and we plot it as a point cloud, color coded according to depth. And this idea of trying to identify trajectories is basically what you can see also for the problem of motion segmentation. On the bottom left, we see the events in red and blue in space-time. And we clearly identified that the events that are generated by one car, they have kind of like an oblique. They are tracing this oblique direction. And the events that are triggered by other cars, they are following a different direction in space-time. So we want to fit a motion model to each of these trajectories to try to segment the scene into different objects. So there are 3 cars. These are the colors, the blue, red, and yellow. These are 3 clusters of events. And the 4th one is that the camera is also moving. So that's the green one. I think I'm going to skip it in the interest of time, but basically these focus measures can be used in unsupervised learning to learn optical flow and replace the photometric loss in normal cameras. So in terms of multi-agent scenarios and event cameras, I don't know, my personal opinion is that we are not there yet. We need to increase task complexity, and it's kind of in line with the words that Eduardo said at the beginning at the opening of the workshop. We need to define another layer. I think we are still in an emerging field in event-based vision. We're still, especially in computer vision and robotics, event cameras were commercially available only 10 years ago, and we are still developing the technology. Mostly low-level vision problems is what we are targeting or addressing. And we need to build more higher level and complex systems. And for that, we need new methods and data sets. So to answer the question how to solve it with events, and not only that, but how to do it on a power budget. We've seen that the scenario plays a big role. The camera motion has a big influence on the events. And we are, I would say, in the current state of the art, we are exploring both handcrafted and learning-based methods to try to solve these low-level vision problems. But learning methods are, I guess, becoming more dominant. And for that, there is a big interest in trying to leverage realistic simulators of these sensors. It's very important to have a good simulator of the event data because it's a quite different type of data. And also trying to leverage as much as you can what you have already learned from image data, not just throw it away. So multimodality, as Andrea Cavallaro was pointing before, it's very important. There is a lot of going on in fusing images and events, but I really didn't have the time to talk about it. Ideally, these are low power sensors, and you would like to combine it with neuromorphic processors if you want to yield efficient agents. Yeah. And to conclude, I hope I have provided an overview showing that event cameras offer many advantages to tackle difficult scenarios such as high speed, high dynamic range, low power in the case of monitoring. In the case of stationary cameras, as you have seen, they provide a complementary information to the frame-based cameras. The frame-based cameras, they pick up on the background, and the event-based cameras are mostly picking up of the moving objects. I only talk about one way to process the events, this idea of focus maximization or event alignment. That is a simple and effective way of processing the event data to solve multiple vision tasks. And there are many open problems, and I hope you join us in this endeavor, researching and trying to solve problems with event-based vision. And here are some references. We have an overview paper that was accepted last year at PAMI. We keep a repository with resources, so papers, code, datasets, companies, and videos. And I recently developed a course at TU Berlin, and the material it's available online. And I thank you very much for your attention, and would like to conclude my talk at this point.
Okay, thanks a lot for the nice talk, Guillermo. I see some claps here in the audience. They're shy to unmute. So let's go to a couple quick questions because we are getting a little bit behind the schedule. So let me see if there is anybody in the audience, any hands raised. Eduardo, yeah, so please go ahead.
One quick question, Ayo, because, well, I guess what you mentioned is that when the camera is moving, the issue is that the amount of events is very high and the complexity, the computational time becomes an issue. Well, I guess from a robotic perspective, let's say, if you have the camera on hand and you don't have this knowledge, you may not be able to do so. But let's say that you had it mounted on a robot and you knew the motion or the inputs, the motion inputs to the robot. Would it be easy to filter events, or to filter the events that you know that they are caused because of this motion? Or do you think it would be easy?
That's a very good idea. Yes, actually, you can do it. If you have an IMU, you can do video stabilization. I mean, some papers back when the IMU was being integrated in the sensor, this was one of the first applications, video stabilization with events. The thing is that you can stabilize the events that are coming from the rotational motion, not the translational part. But then you cannot really throw them away because you don't know which events are generated by rotational motion and which ones are generated by translational one. You can stabilize it, but I don't think you can throw them away. So it's still good. You can,
I guess it's kind of an optical flow, right? So you can imagine if you're moving to the right, you're going to have events, well, positive, negative events going, let's say, if you're moving to the right, to the left. So I guess probably you are throwing away valid or useful information as well, but would it make sense? Okay, so whatever is moving opposite events in opposite direction of motion, skip them.
Yeah, no, I think it makes perfect sense, but what I'm saying is that I'm not sure if you can throw them away. You could stabilize them and convert them into some representation that it's stabilized and use that stabilized representation, but suppressing them completely, there are other ways to do it. I guess there was a paper doing this for obstacle avoidance, when you have the drone and you throw an object at it, you are trying to remove all the events that are coming from the ego motion, looking at the timestamps. But yeah, it can be done for some specific scenarios, yes.
Okay, thank you.
Sorry, also following a little bit this question. So you mentioned that this moving cameras is especially challenging because it mixes the events. You don't really know where they come from. So the representation that you have explained, the one that you have been working, this focus maximization based representation. So it's particularly, well, it's a question. I mean, do you think it's then particularly suited for this problem? Because if I understood correctly, then you start the iterative process in the, let's say, ideal situation where all the X and Y coordinates at every timestamp are aligned, and then you iterate until you get sharper. So if there would be no motion from the camera at all, there wouldn't be that much benefit, right? From or am I wrong?
So
you know what I mean?
Let me try to see if I can rephrase it. So this this intermediate representation, it's actually it's an image of warp event. We are converting events into an image, but it's an intermediate representation because the goal is not to have the image. The goal is to estimate the motion parameters.
Yes.
And if nothing is moving in this, I mean, if the camera is static, the motion that it's creating the events will be by moving objects. So you would use this to estimate the motion of moving objects, but not the motion of the camera. If you want to do both, that would be what it's here with the motion segmentation. The camera is the green, corresponds to the green, events on the bottom right, and the moving objects are the other ones, the blue, the red, and the yellow. It's being able, by looking at the trajectories, you're able to estimate the different motion in the scenes.
Okay, so it helps you distinguish if it's generated due to ego motion or due to scene object motions.
Yes.
Okay.
This is one representation, but I guess there are many other representations that would be applicable and try to solve this same problem.
Okay. No, this it sounds very interesting. To use this as part of the loss, so you can include it in the loss. So thanks. I don't know. I actually had another curiosity. I don't know if there's any other question. I don't want to take all the all the questions, but if not, I can ask. It's a little bit more open question because you mentioned at the end that we definitely need to have more challenging scenarios, right? And one problem, as usual, is to have data sets to evaluate. And then with event cameras, it's well, I would say even harder, right? Because even if you would like to annotate manually the events, it's impossible. You need to have some RGB image synchronized or something. So we have seen there are some data sets being created by recording screens of known actions or objects, or other data sets created from simulators. I don't know, do you have since you have a lot of expertise with events, do you have an opinion on what's the best way to go? I mean, you mentioned leveraging the simulators, so I kind of intuit that's maybe your vote, but I don't know. I'm always curious about these other approaches, like recording real data on a screen, synchronizing with an RGB camera to use pseudo labels, or what do you think of all these options?
Yeah, well, I think it's a big problem, and we try to address it with many different solutions.
Yeah.
And hopefully, with all of them, we try to narrow the problem. The sensor, it's highly dynamic. I mean, it has many nonlinear effects, and it's very difficult to characterize. We really don't have a very good model of the noise of the sensor. So if we had a very good noise model of it, we could implement a very realistic simulator, and we could just transfer whatever we do with the simulator with real data and be fine with that. But actually, that's not the case. Recently, there is a simulator called, I think, B2E from Toby Delbruck, the same guy who produces the camera. He knows how the circuits is working, and therefore tries to come up with a realistic, more realistic simulator. Before, I was working on simulators, and we were just trying to do almost like thresholding, right? The very simplest model to do. Now we are getting more and more technical, and we are improving the simulators. But there is also the question about the synthetic to real. There is a gap. I don't think any simulator will get us to where we want. We always need the real data, and especially with these sensors that they have so many bias currents that are going inside, and we are really not yet tuning. I mean, as soon as you start tuning all the parameters of the camera, as you would do with the parameters of a standard camera, probably the simulators that we currently have, they are not working. So I think we need both. We need both the simulators and real data. And I agree with you that acquiring ground truth data is very, very difficult. If you want to have, for example, microsecond resolution optical flow, how do you do it? All in, perhaps with a motion capture system and with a motion field, but it's very, very difficult.
Yeah, okay, thank you. So we are still, as you said, trying to get from all possible sources to get data. Okay, thank you. I think we have a question in the chat from Colin. Do you want to ask yourself, or you can read it, Guillermo.
I think there are two. There is one from UPenn called MVSec. Multiple vehicle. This is one from UPenn, and the other one is there is one from UCH about FPV racing. FPV racing dataset. These are recorded with Davis 346 mounted on a drone, I think. Those are the two that come to my mind. Maybe there are more, but these are the ones that come to the table.
Thank you, Guillermo. Thanks. So I think we should move to the third talk of the session, because we are catching up. Well,